So, hey, my name is Sina. Thanks, Piper, for the shout out. So I want to motivate the talk by showing a diagram that Alexei generated. As you know from the previous talk, for stateless clients, you need to send a witness alongside with the block. And I just have part of one of these witnesses. And like you can see the tree structure here, like you can see the hashes, the nodes, and whatever. And this big block here is a code block. Like this is a contract code. So you need to send contract codes with like any contract that you use in a transaction needs to be sent in a stateless block. And as you can see of the size, they can be quite big. And this is what we'll be attacking. So I will be going into the weeds. We'll see some of the quirks of the EVM. By the end, like if you follow, you can just jump in and start attacking the problem yourself if you were interested. And I will also share some data that we got from some of the mainnet blocks that show that the approach we will be taking here will cut down the size of the stateless blocks somewhat. So stateless blocks are big. The witnesses that you need to send include all of the accounts of the tree structure, like all of the storage items and all of the contract code. I won't go into the intro of stateless because Piper already talked about that. But I will show you some data from TurboGel, like from Igor and Alexei, that was generated recently. These are from some of the most recent blocks. And like the blue on top is an average of how much these block witnesses like weight, basically. So you can see it's, that should be megabytes, sorry. So it's on the order of 800 kilobytes to 1.5 megabytes. And the brown line here is the hashes that you need to send for the Merkle proofs, which is right now the biggest contributor to the block size. And the next one is contract code, which is around 1/3 of the whole witness size. And after you already realized that a possible change that we'll be doing in the stateless roadmap is to change the tree structure from a hexagonal tree to a binary tree. And that would reduce the number of hashes that you would need to send by almost 1/3. And then contract code will become the biggest contributor to witness size. So if we can reduce that, we'll be reducing the overall witness size. And one reason why this would matter to dApp developers is because if we don't do this, then you would need to pay gas for every byte of a contract that you're invoking. So let's say you're invoking a contract that weighs 24 kilobytes, that's the maximum size for now. You would need to, let's say, pay 72,000 gas. And if the contract is smaller, then somewhat smaller. But the crucial point is that any contract that your transaction invokes, you would need to pay gas per byte of the total amount of contract size. So the intuition here is that a transaction only invokes part of the contract codes. Let's say you're interacting with an ERC20 token. You only want to call the approve function, which is a small part of the whole code. Why do we need to send the whole contract code when we are only using one function of it? So what we want to try here is to only send the parts of the code that are necessary to execute a transaction and some proofs that prove their validity. And we do this by like chunking the code and creating a Merkle tree out of these chunks. And during like a block transmission, we send only the necessary chunks and their proofs. So imagine we have a miner and somebody wants to create a contract. Like this is an imaginary bytecode that somebody is creating. So the miner, this is the runtime bytecode, not the init code, by the way. The miner, as of now, it does a single pass over the bytecode to check for jump desks. If you know what they are, so jump desks are the valid locations in EVM bytecode where you can jump to. It already does a pass over the bytecode to determine this. Like during the same pass, what we would be doing is we distinguish what we call basic blocks, and these are blocks of the code that don't contain any control flow change. Like there's no jumps, no return, no stop. So whenever we come upon one of these opcodes, we stop the block and we start a new one. And the main characteristic of these blocks is that either a block starts at the first byte of the bytecode, or the first byte or the first opcode is a jump disk. This is crucial, as we will see later on. And later on, we don't want to have too small chunks. I will explain why later. So therefore, we kind of merge these basic blocks together to get a minimal, like a minimum size. And in this diagram, this minimum size is 32, as you can see here. So this bytecode, let's say the miner did a pass and determined that these are the 4 basic blocks. All of them start with jump test. Now, as you might know, the Ethereum state contains like a tree. This is the tree. It's not an accurate picture. Like we have the hexagonal tree and so on, and just like, yeah, it's a tree. And in the leaves, you have the accounts, which have these fields like state root, balance, nonce, and code hash. So the important thing is that contracts, like you store the hash of a contract code in the leaf of the state tree. But what we'll be changing here is that instead of storing the code hash, what we do is we make a tree out of the chunks. So these are the 4 chunks of our bytecode. We make a Merkle tree out of it. The keys of these chunks are the first byte of, like this. Oh shoot! Sorry. Yeah, this is the index of the first byte of this chunk. 42 is the first index of the other chunk, and we'll use that to store the chunks. Like we use those as keys, and we store the root of this Merkle tree in the account. And so the contract is now deployed. It's on the chain, and a user comes and wants to use this contract by sending a transaction to it. So when the miner wants to include the transaction, it has to execute it, and while executing it, it keeps track of which chunks in the contract have been touched. So let's say this specific transaction touches the first chunk and the third chunk of the contract. So what it does is, in addition to sending all of the accounts and storage items necessary for the transaction, it also sends these 2 chunks as well as the hashes. So all of the rest of the Merkle proof that prove the validity. And so this multi-proof is included in the block. Now the block and the witness propagate across the network, and a stateless client that wants to verify the block receives the transaction, verifies the proof to make sure that it's the hashes match, and then it can reconstruct the bytecode because it knows the full length of the bytecode, and it knows the index of the first byte of each chunk, and it leaves all the other chunks 0. And it can do jump test analysis safely because it knows that every chunk starts with a jump test. So a stateless client can receive only those parts that were necessary and still execute the transaction safely. Now, to test our intuition that transactions only use a small part of the contracts code they invoke, we did some experiments on 50 mainnet blocks, and you can see that the blue lines here are how much code you would need to send for a block if you were to send the whole contract code, and the red line here is how much the chunks and witnesses you would have to send if you were to do Merklization. And you can see that we would get like 40 to 60% saving if we were to do code Merklization. And this has the consequence that when we want to do gas repricings, you wouldn't need to pay for the size of the contract that you're invoking. You would only pay for how much of that contract you're using in the transaction. Now, to where to go from here, we can experiment with a few things like the minimum size of these basic blocks, and we can use, like in my experiment, I use a hexagonal tree to generate the proofs, but we can use a binary tree which will reduce the proof hashes by 3 times. And something else that is also exciting that others are experimenting with is not. So I use like jump test as a boundary between the chunks, and to see why this was important is because imagine you have this bytecode here, and you divide it by arbitrary borders. So like let's say we have a fixed size, like each chunk is 32 bytes. It could happen that you have a push at the end of one chunk, and the next chunk starts with a number that is exactly the same as upcode jump test. This way, when the stateless client receives these proofs and the chunks, it wouldn't know if this is a push data or a jump test. So it could happen that they would execute the transaction differently from clients that have the full code. And in order to fix this problem, there are multiple ideas. One is to add some metadata to each chunk so that you would know how many of the first bytes are data or opcode. Or what Alexei is pursuing is to validate the contracts statically, so that before, like during runtime, you can be sure that every jump goes to a valid jump test. So basically, this would mean effectively like disabling dynamic jumps in EVM. Yeah, that was it. Thank you. Questions?
So in your chart that compared the full witness size to the chunked witness size, does that include like all, like if the same contract is included multiple times, does it include them merged into one proof, or how does that work?
So yeah, this is in the whole block. Yeah, we deduplicate the contracts. So if you're using the same contract multiple times in a block, then you would only send it once.
Does this have changes to sort of like smart contract dev and compiler design, things like that?
So the changes would be, I mean, you would need to, again, gas repricing is a thing. You would have to probably change the price of coal, and also any other opcode that uses contract code, like Xcode hash, Xcode size, Xcode call, so these would be affected. Compilers could maybe optimize for this by, like, if they knew what is the chunking scheme, they could localize the relevant, like the parts of the code that are executed together. They could put them close to one another so that in the Merkle tree, those chunks would be close and would share a lot of the proof. This is some optimization that compilers could do.
One last question. Okay.
So I'm not sure this is an issue, but it's the miners who produce the proofs, but if I send a transaction, I have to pay the gas relevant to how much code I will use. Sometimes I don't know that, because which code will get touched is determined by what order the miners include the transaction. Can you just comment on that?
So yeah, during the transaction execution, you could only we could charge conservatively. So we could consider the worst case, and at the end of the transaction, could maybe do a refund. Yeah.
I think there, in my current model, we're not going to be increasing the gas cost of the specific operations like call and Xcode data. Instead, I would suggest to introduce a separate gas counter which only going to account for the increase in witness. So we decouple that from we don't have to mess about with the, let's say, making call dynamically cost. So unpredictable cost of call. No, I don't think it's the right approach, and I think we should instead do the second counter, where as we go along through the transaction, we account how much witness we've produced so far, and charging gas. And it has some other issues as well, but yeah.
Yeah, as you see, these parts are still being specified. There is no specification. This is just how I did it. But of course, yeah, I mean, we are discussing these things further this weekend.
So thank you very much, Sina, for your talk.
Thank you.